My name is Will. Today I'm going to tell you a story about computation and architectural design. It's very personal to me, and it's what I do at work, but I also love what I'm doing. This is a graph that I will come back to just a little bit later. So I was trained as a traditional architect, went to undergrad for a professional degree, and they teach you the way of architect, making drawings and representations of the building form. So you see this, you think of architects. And after that, I went to grad school for a concentration in digital technology. And that's where I was exposed to this whole side of architectural design, where computing and knowledge in computing really is informing new ways of architectural design approach. So right now I work at an office in New Haven, PechaKucha Architects. The office does a lot of high-profile, high-rise buildings. This is actually Salesforce Tower in San Francisco, probably the tallest building west of the Mississippi River. But the office does all kinds of buildings in different markets. This building you're looking at is actually a healthcare building, but I'm not here to try to sell the office's service, but I do want to draw attention to the kind of pattern that you see and the sort of unconventional shape that's happening nowadays. So modern buildings really demands a new way of geometric control and the design approach. You might be familiar with CAD software. It's very much the status quo of design production still. It's not particularly intelligent. It's just drawing on digital paper. So the field needs to advance. So this graph is actually what was on the first slide. It's something called a visual scripting tool. This is introducing architects into this world of these nodes and spaghetti wires where you can string up a whole sequence of them and then generate your shape and form per particular logic. So in fact, architects have been rationalizing geometries because of the constraints of construction. So this process goes perfectly into that kind of spaghetti wire sequential parametric design, as we call it. With that, with each step along the generative of the shape, you can understand the performance and the metrics of your building form, and this is actually an interface where it tries to optimize the design result, given that kind of a feedback loop. You can see that it gets slightly better each iteration. And then this is an example where we optimized, we wanted to keep the curtain wall facade, the glass within, the warpage of the glass within manufacturer warranty, but at the same time we want the most dramatic kind of curve. And we had to make this tool. You can see on the left this kind of little dashboard that tells you all the numbers. It's something that architects kind of have to make themselves. Softwares don't come with this because the specificities of each project is just something that software companies can't predict. So with that kind of dashboard, we can even just like write up our own little queries into a database and then kind of marry abstract data with the geometric shapes and objects. So in this case, you can look at history of a building or even energy consumption if you have the data for it. And then one of those metadata is, of course, geolocation. And in this case, we can program something that helps you understand the solar performance of your building, heat gain, or number of exposure hours, things like that. So sometimes these things create interesting artifacts. This is actually, you're looking down a bunch of buildings. Those are the shadows that it casts across a time period, and it's a composite. So really, I've heard arguments that these kind of analytical things are really something that the engineers handle. The contract is set up for that. But I argue that with the sort of understanding of the components of a building and the tectonics of architecture, meaning how things come together, like this, a panel on a building facade. With the understanding of these, architects and really start to improve the design delivery from very early on in the project. And of course, architects are not only expected to make pretty pictures, but also make things work. So what do we do if we're looking at a class schedule and the client asks us, how many classrooms do I need? So I think the answer is, computing. So for that exercise, I, visualized the data first. I did a whole bunch of geometric intersections and algorithm, things like that. And in the end, I got a whole set of results that accommodate that kind of class schedule, and then I visualize it again and can look at utilization. So to take it one step further with computational skills, designers can even start to simulate nature. What you're looking at is actually kind of a rain flow on top of a roof. Before you have to go to engineers for this kind of thing, it's not only very expensive, but also you get turnarounds and overhead, and it's just kind of an outdated mode of doing things. And of course, this is even one step further. I pulled these images from the internet, so there are designers starting to look at the hottest topics in the tech world. I don't even understand myself. So I guess at the end of the day, a lot of people tell me, this is very far-fetched, this is not real. But I think, in case you don't know, architecture design is kind of an industry that moves incredibly slow forward. So this is the kind of impetus that we need to really drive the profession forward. So thank you for your attention.